Chapter 19, question 7 is kind of a mouthful. An unknown concentration of sodium thiosulfate is used to titrate a standard solution of KiO3 with excess Ki present. Suppose 16.05 milliliters of Na2S2O3 was required to titrate the iodine formed from 22.1 milliliters of 0.0121 molar KiO3. What is the molarity of the thiosulfate solution? So this is actually a titration problem where we're calculating how much concentration is like the unknown. There were two equations or two reactions that were given. IO3 minus, that's the same thing as KiO3, but we just took the potassium off. Plus 5I minus plus 6H plus becomes 3I2 plus 3H2O. And then I2 plus 2S2O3 2 minus. That's the same thing as sodium thiosulfate. We just took the sodium off. Becomes 2I minus plus S4O6 2 minus. Okay. Now we are looking for the unknown, but we do have the amount it took to titrate this. So let's start with what is known. I know that I have a concentration of 0.0121 molar KiO3, and I know it took that much long for it to titrate. So I'm going to start with 0.0121 moles, and I'm going to change KiO3 just to IO3 because it's the same thing, and I also want it to match what's on the reactions underneath. And that's moles per liter. I'm trying to get rid of those liters because I want it just to be moles, because I need to use stoichiometry to go from IO3 to S2O3. So it took 22.1 milliliters for this to titrate. So I have to convert that to liters. So I divided it by 1,000. I'm just going to put a 1 down here because it's a placeholder. So those liters are going to cancel, and I'm left with moles of IO3 minus. But I'm trying to get over to moles of S2O3. So let's look at this first equation. I want to have moles of IO3 on the bottom so I can then have those cancel. But there is no S2O3 in the first equation, so I need to actually convert it first to something that is common between both reactions. So that could either be I2 or I minus. So I'll just convert to I2 first. So if I'm looking at the first reaction, it takes 3 moles of I2 for every 1 mole of IO3 minus. And in the second reaction, I want to have moles of I2 cancel, and I want moles of thiosulfate on the top, so I'm left with that because I'm looking for its concentration. So for every 1 mole of I2, there are 2 moles of thiosulfate. So let's just see if everything cancels. Those liters will cancel, those moles of IO3 will cancel, and those moles of I2 are going to cancel. So I'm just going to be left with moles of S2O3 2 minus. But I'm looking for concentration, so I need to then convert that to concentration. So when I do the math, I get 0.00160 moles of S2O3 2 minus. Now, if I'm looking for concentration, I have to have moles per liter. So they gave us the amount of the unknown sodium thiosulfate here. So I just need to convert that to liters, 0.01605. And so my concentration of S2O3 2 minus is 0.0999, or just 0.1 since I rounded. Chapter 19, question 8. Consider a galvanic cell in which aluminum 3+ is reduced to elemental aluminum. So they were nice enough to tell us that aluminum is being reduced. So that's the cathode. And magnesium metal is oxidized to Mg2+. So that means oxidation is happening at the anode. So let's write these reactions to where they make sense. So if aluminum is being reduced, it's going from Al 3 plus to Al solid. And I have to put 3 electrons here for that to be balanced. And magnesium is going from Mg solid to Mg2 plus. All right, so those electrons on both sides are not the same number. So I have to multiply both of them by a certain number to get them to be the same. So if I do that, I'm going to multiply by magnesium by 3 and aluminum by 2. So by doing that, that's going to change this number to 6. So I can then cancel out and bring down for the overall equation. So I have magnesium solid, as a 3 out front, plus 2 aluminum, 3 plus, becomes 3 magnesium, 2 plus, plus 2 aluminum solid. Chapter 19, question 9 says write the half reactions as they occur at each electrode and the net cell reaction for this electrochemical cell containing tin and silver. So they gave us the way the voltaic cell would be written in cell notation. Usually they put the anode on the left-hand side and the cathode on the right-hand side. And what's happening in solution is kind of happening how it's written. So silver, sorry, that's 10, SN. So it's going from a solid with a charge of 0 to a charge of 2 plus. So it's being oxidized. So I'm going to put the 2 electrons for it to be balanced. And then silver is going from a +1 charge to a 0 charge. So it is being reduced. It gained 1 electron. But we have to make those electrons balanced. So if I have 2 electrons over here, I also have to have 2 electrons over here. So I'm going to multiply everything by 2 for that all to make sense. Because I want those 2 electrons to cancel, and I'm going to bring down everything else for that overall equation. So I have 10 solid plus 2Ag plus becomes Sn2 plus 2Ag solid. Chapter 19, question 10 says calculate the standard cell potential for this reaction shown below. And in the notes I gave you a link to a table with all of those cell reactions, and these are the ones I got for those. We're going to need to know the equation E cell is equal to E cathode minus E anode. So let's look at the equation here and figure out what is the cathode and what is the anode. So at the anode, that's where oxidation is taking place. And the cathode is where reduction is taking place. So let's look at this equation. Copper is going from a charge of 0 to a charge of +1. So copper is being oxidized. So copper is going to be the anode. And then silver is going from a charge of +1 to a charge of 0. So it's gaining 1 electrode. So silver is being reduced. So I'll just look over here and pick the values for those two and plug that into this equation. So E cell is equal to my cathode, so that's my silver, minus my anode. So I get 0.28 volts.